Spin around through the house.
You did.
I haven't minded the video.
What's your issue?
What came from
Oh snap. That's not good. We'll talk about that later. Okay, here we go. So, from the top. With that, let's take a look at these two problems. Today we're actually going to kind of reverse. We're going to do these two problems and go back and finish off some of the practice we didn't do yesterday, because I want to make sure we feel really good about graph transformations. And yesterday we didn't really get to talk as much about dilation, stretching, and compressing. We only really talked about shifting around. Okay, so we're going to recap all that stuff, close up yesterday's lesson, because today's lesson is a little bit shorter, and we should be able to just use the last piece of class to kind of cruise through today's lesson. I think some of y'all have already done some of the equations we're going to do at the end, so it should go a little quicker. Okay, so let's talk about these. I know these graphs are kind of, the squares are kind of small, and it's hard to draw, especially when you're at like 1. So kind of stick with looking at my picture up here, and let me know if you can't see something I'm drawing here, because the dot has to be in a specific spot, and it might be hard for y'all to see. So let's talk about this function. What is the starting function before the transformations? What is the beginning function that we're starting with? Adrian? Oh yeah. So where it starts is 0, 1. The intercept is 0, 1. But the function f of x equals b to the power of x, what's our starting b to the power of x in this equation? What's our base? Maggie? 3 to the power of x is our starting graph that looks like this, right? And then we subtracted 4 on our exponent and added 1 on the side, and so we transformed this graph. So the graph of 3 to the power of x is exponential growth. It looks like this, because b is bigger than 1, and we have a positive x up there. Now we're going to go ahead and we're going to do some transformations. Raise your hand if you can tell me what happens when I subtract 4 on the inside like that, not on the outside. Justin?
It moves to the right.
Moves to the right. It moves forward 4. So our graph that looks like this, we're going to pick up and move it forward 4. Okay, and then what is the plus 1 going to be doing on the outside? Samantha?
I think you move it up.
Up 1. Adding or subtracting on the outside moves it up and down, right? So then we're going to go up 1. So we want to go over 4 and up 1. That means since we're shifting, this intercept is going to move over 4 and up 1, and my asymptote is going to move over 4 and up 1, okay? So if I go over 4 and up 1, this point that started at 0, 1 is going to go 1, 2, 3, 4, and up 1, and that point is going to be floating over here. It's not an intercept anymore, but it's going to be floating over here at 4, 2, right? Because if it went up 1 and it started at 1, now it's going to be at 2. Okay? And then our asymptote, if our asymptote used to be at 0, if it goes over 4, it's still 0, right? And then it goes up 1, so now it's at y equals 1 right here. And so think about this as your new starting point. From that point, we're approaching our asymptote of 1 on this side, and then we're shooting up to infinity on the other side. So if you had trouble kind of drawing that, it might help to move your intercept and move your asymptote, and then draw it approaching the asymptote and approaching infinity on either side. Okay? So that would be our first one. Our second one, the beginning function is not an example like 3 to the power of x. What is our second function, starting with before the transformation? What function do you see without the extra numbers? Jimmy? The natural base e to a negative x. So is that an example of exponential growth or decay? Which graph are we looking at? A little louder? Decay. Okay, yeah. Exponential decay. So we're looking at this graph, facing this way, crossing through 0, 1. And if we subtract 4, where is it going? down 4. So we want to take that graph and we just want to go down 4. If it was subtracting 4 up here, it would go forward 4. If it's subtracting 4 on the outside, it goes up or down, it goes down 4. Okay, so that means, again, both your asymptote and that intercept, because I'm picking up the entire graph and moving it down 4, both of them are going to move down 4, right? So if our intercept was at 0, now where's it going to be if it goes down 4? Zero, go down 4? Okay, sorry, I thought I heard like negative 1.
Don't we start at
It should be at -3.
Yeah, because we start
The
at
asymptote was at 0, goes down 4. I think you're talking about the point, right? The intercept, I agree, the intercept is going to go down 4 and go from 1 down 4 would be at -3, okay? And then again, using this point in your asymptote, it's approaching on that side and going up here. So your new intercept is 0, -3. Your new asymptote, go ahead and label these. Oh, thank you. Yep. I was like, so many hands. Something must be wrong. Thank you. Decaying, so facing that way. And this is at -4. Happy? Did I miss anything else? Okay, so it's decaying, shifted down 4. So it's at -3 the point, -4 the asymptote. Okay? Notice that the distance between this kind of like critical point, this asymptote, and our critical point, this intercept, is 1, right? Because I'm not multiplying times this anything, so our starting point is 1. You're going to see now, we're going to go look at some dilations. We're going to start to see that distance change as we stretch and as we shrink the graph, right? Picture stretching something, it's going to like literally be a longer distance. Shrinking it is going to be a shorter distance, okay? So we're actually going to flip back. I'll come back to today's lesson in a second, but we're going to flip back to some of the practice from yesterday that we didn't get to. We finished that matching activity, or at least got started on it, but we're going to pick up on the 4 examples that were on the back and talk about what happens when we have a dilation or a number being multiplied in front of our graph, okay? So take a look at this first one. We've got e to the power of x. So we've got a base of e, which is one of the numbers we're going to see a lot in this unit, but that's the same as having any other base to 100, something like that. Is this an example of exponential growth or decay? Growth. Okay, so you're picturing in your brain this graph, you just know it's going to change a little bit, right? If you have a 1/2 in front, I'll go ahead and show you the graph. I want you to take a look. If you graphed it on your calculator, it's going to look like this. Really quick, talk to your neighbor, tell them what's different about this graph from our original e to the power of x graph. Talk to each other. What's different? All right. Hands up. What do you notice? Hands up. What do you notice? Karen? The intercept is now, and I know this is hard for y'all to draw on yours because they're so small, but the intercept is not at 1. The intercept has been like shrunk or condensed. Isaiah. Shrunk or condensed to 1/2. Stick with me, stick with me.
Okay.
What's tricky about this is it is not shifted from 1 down 1/2. Did the asymptote move at all? Did the asymptote move at all? It's still at 0, so this distance right here between your intercept and your asymptote just shrank from 1 to 1/2. Okay? So whatever that number is in front that you're dilating by, your factor that you're dilating by, becomes the distance between that point that we talk about and the asymptote. Okay? Okay, so using that, let's write down some of these characteristics. We're going to kind of talk through these two, then y'all are going to do the 2 on the bottom on your own, okay? And these are tough, so you got to really make sure you're still with me. Your brain is engaged. You're not just sitting there writing things down, okay? Still on my clicker. Let's take a look. So, domain and range. By shrinking it, did I change my domain or my range? So it should be the same as yesterday, and we wrote that down a lot, so it should be familiar in your brain, or you can take a look at yesterday's example or my poster. The domain went from negative infinity to infinity. The range starts at our asymptote, which is at 0, and goes to infinity. So our asymptote is at y equals 0. Again, that did not move with the 1/2. It just shrunk, and now the intercept is at 1/2, and the distance to the asymptote is smaller than it was before. Okay? And then the end behavior on this side, since it's still asymptote at 0, it's approaching 0. On this side, where's it headed? Positive infinity. Oops. I don't know why this is. Cool? Okay. So let's talk one more together about an example that is going to not just have a dilation, but also have a shift. Okay? We're going to go through this one, see what happens. If I am looking at this function, it's the same e to the power of x, so it's still exponential growth. The factor of 3, let's wait and we'll talk about the 5 in a second. This 3 out front, similar to the half, who can kind of summarize what they think is going to happen based off of what we saw with that first graph with the half. What is the 3 going to do, Isaac?
It's gonna skip the
Intercept?
intercept, yeah.
The intercept is going to be stretched up from 1 to what? To 3. So it's no longer going to be the asymptote and 1, it's going to be the asymptote and 3. Did your asymptote move?
Yeah.
No. Not for the stretch. It will, Jose, in a second when we shift it down 5. But for the 3, if we just focus on 3 e to the x, this dilation, just like this 1/2, does not influence our asymptote. Okay? So for right now, I'm going to sketch it off to the side. For right now, with the first part of the transformation, we're just looking at something that now looks like this. See how it's up there at 3, going all the way from 0 to 3, rather from 0 to 1. Okay? Then we're going to take that graph, and we're going to subtract 5, which means we're going to do what? That's like what we did on the do first. What does minus 5 outside do? It's going to go down 5, which now means everything's moving. The point and the asymptote, we're going to go boom, and we're going to go down 5. So let's start with the asymptote. If the asymptote is at 0, and we go down 5, it's going to be negative 5. 1, 2, 3, 4, 5. Okay. If our point is up here at 3, and it goes down 5, where are we going to be?
Right.
You're up at 3.
Oh,
You're not
okay.
at 1 because we
Okay.
stretched it. We're up at 3. We go down 5. We're going to be at negative 2.
Come on,
Notice the distance between my intercept and my asymptote is still 3. See how there's 3 little boxes between them from our stretch of 3? Just like the distance between my asymptote and my point here is 1/2 because of the 1/2 in front. Okay, so we end up with something like this, and it's growth. So I'm going to approach the asymptote on that side, head to infinity on the other side.
Is it a 2 or a 1?
The point? At, you mean negative 2 and 1?
Yeah.
So if it was up at 3 and we go down 1, 2, 3, 4, 5, we're going to be at negative 2. Cool. Okay, so then filling out the other things really quickly, we end up with domain and your range. Your asymptote changed, right? So your range is going to change and start at the asymptote, negative 5. So your asymptote is at negative 5, which means your end behavior is going to approach the asymptote and infinity. Okay? Using those 2 examples, we still got to get to today's lesson. So kind of stick with me. I want you to see how you do on the 2 at the bottom. And as if this is feeling weird to you, call me over and I can try to kind of explain in some different ways. But try the 2 at the bottom, and then we'll go on to today's stuff. Go.
You get a question.
It'll approach the asymptote, it won't go below the asymptote, unless like we literally reflect it and flip it in a whole graph that's below. And then it'll be approaching it from the bottom. But it won't just cross through it. Yep. Okay, let's jump through it. Okay. I know. So, for this one, our original function is just this piece, 2 to the power of x. What does that look like? Which one? Top or the bottom?
The top.
The top, it's exponential growth. So we know we're starting at 0, 1, and it's growing. Okay, now we got 3 things we gotta do to it. We're gonna work from the inside out. Move up 5, we're gonna work from the inside out though, so that we don't do it in the wrong order. So we're gonna move first to the right 2. Okay, so we're like right here. We're not gonna draw it yet, but we're right here. It's still approaching 0 and then heading up here. We haven't changed our asymptote, our gap is still 1. Okay, now we're gonna deal with the 3. What does the 3 do? It stretches it. So our asymptote stays where it is. It's not shifting up 3. Our asymptote stays here, but instead of this being a distance of 1 from our point to our asymptote, now this is up at 1, 2, 3. So it's a distance of 3 from our point down to our asymptote, but our asymptote's in the same place.
Let's say this is like at 1/2, we can multiply that by 3.
Yeah, but it wouldn't be a 1/2 because it always starts at 1.
So why don't you
That would be if you added 3 on the outside, you would shift the entire graph up through the asymptote. This 3 is, you're dilating it by a factor of 3, it means everything is 3 times as big. So like you said, this is 1, so 3 times as big, so it's up as 3. But it's never going to be starting anywhere else, it's going to be starting at 1. Okay, so we're up here, and then this is still going to 0, and then this is heading up here. Now, we're going to go where? Up 5, which means not only is this point going to go up 5, but your whole asymptote is going to shift up 5 too. We want to maintain this distance of 3, this is up 5. So if we go up 5 from here, 1, 2, 3, 4, 5, we're going to be up here at 8. And if we go from 0 up 5 for your asymptote, 1, 2, 3, 4, 5, we're going to be at 5. And then notice this still has a distance of 1, 2, 3 to your asymptote. I think I got those in the right spot. They're so small. But it's approaching it. We're actually should get close. Doesn't touch 0. So notice that's why we put a parenthesis on 0.
Oh, okay.
7?
Yep. You don't scale by 2. 2 is your base. 2 is like the E. We scale it by what? 3. The 2 is the base, which remember like I talked about yesterday, all of them are going to have that graph, whether it's 2, whether it's 100, because 2 to the power of 0 is the same as 100 to the power of 0. They're both going to cross at 1. So the
it doesn't affect anything, right? It's just right.
The base is going to influence like all those numbers, like how this is getting small and how it's getting big. So you graph on your calculator, the power of x, and see the difference in the graph. But both of them are going to 0, 1. Both of them are going to have some. It's not going to be anything. It's okay for sketch for me. Whether I hit the power of x, this one, then I hit 2 times 5 or 2 is the thing for your.
Oh, that was at most 30
Decay to
Stretched up 3, and then you added 5. Oh, yes. Because it's not 1 lower, it's 3 lower. No, you didn't. You both did it wrong.
did it wrong.
We did it wrong. Both of us did it wrong. The asymptote. The asymptote is letter P. It moves up 5. So it's right here. And then you shift it up 5.
It is up there.
The asymptote.
Over there. No, those because they put your own paper.
What is she saying? What is she saying?
Talk about the white and moving five.
The what now?
This one.
The Y just that moves to the
I see where you got that.
She's talking about the asymptote moving five.
because it has to do with the amount
Who are you going to? You really went to gym?
Here, you'd be taking the
I don't care.
If you came and explained it, still don't understand.
Jimmy said that the asymptote was up.
Of course it was up.
Jimmy said the asymptote was up.
I moved it up. Oh, I moved it up. What are you talking about? Did you do it? I'm probably wrong.
Okay, y'all, I'm only gonna give you like 3 more minutes on this because we gotta move on to today's lesson. So I'm getting a lot of great questions from around, but make sure you're still working hard. I know that these are kind of difficult.
Thank you. Thank y'all.
Hey, me too.
What's up, bro?
I put negative 5.
negative.
You can do it.
Decay.
And then I'll okay, how are we doing over here? Look, see? So look, the original graph, you're starting from like where? Here. Okay, so we're not going to multiply anything. Make sure this is the same as E. Right? Then you multiply E times anything. No, so we're not going to touch the 2. The 2 is telling us that it's the exact same as the
There, you can go over there.
now, we're going to move this someplace else. Make sure to the right.
What is it?
No, we don't need help.
I'm sorry.
Okay. Now, part one.
I did not say that the question was. I did not say asymptote. Okay. You know what asymptote is?
Okay, then, and that means your asymptote is still the 0. What's the 3?
So you like give me 5.
Just like this. Up from 1 to 3. It basically multiplies it times 3. So 1 to 3, it's going to be up at 3. No. It's going to be up at 3. It's went 2 over, and then you're going to stretch up to 3. You're not shifting up 3. You're stretching up. Right. 2, 3 now. And then stretch the other distance from 3 skid on.
What?
Now we're going to take this graph and shift it up 5. That'll be asymptote.
I said highly.
He go, come on.
Y'all heard that? That's 2. We were at 1, then we stretched up to 3. So we had 2, 3. I'm gonna ignore. And then we shifted up 5, which means we're at 2, 8. We didn't add 3, we stretched up to 3. We multiplied this times 3. Okay, boys, I'm sorry, Isaac here. I gotta keep pushing us ahead to today's lesson. I gotta keep pushing us up to today's lesson. I know that these graphs are challenging, and I would love for us to keep going the entire time with them, but we have to get to today's stuff as well. And so I'm gonna leave you with these two that we're gonna talk about briefly right now, and then I really encourage you to not wait to do this part of the problem set. You saw, I can't talk. You saw your blue problem set right there. The folder's blue. Problem set's white. You should have gotten that, and I encourage you to start those problems soon. Not right now in class, but soon, because Sunday night, Monday before class, this stuff that we did right here is going to be really foggy, and it was already difficult to begin with, right? So really let it sink in tonight or tomorrow by looking at this practice soon. Okay, so this one right here is our normal exponential growth graph, but it was shifted 2 that way, stretched 3, and then picked up and moved up 5, which lands it right here, where your point should have been at 0, what, that's all right, 2, 8. And your asymptote is at y equals 5, which notice means the distance between our point and our asymptote is 3, like our stretch. Now, if you didn't do that problem with your neighbors, it's going to be confusing to see where I got that. I'm not going through every step of it because they take a while to do, but you can check your answer and then check in with me if you have no idea where that came from, okay? With that graph, these would be the characteristics. You can check those off. Okay, on the next one, you've got a stretch of 4, what brings it up to 0, 4, and then you pick it up and shift it up 1, which brings your point to 0, 5, and your asymptote to y equals 1. Again, what's the difference between these? 5 minus 1? So the distance is 4. Same thing like what we stretched it by. Your asymptote and that point should show that dilation and no longer be 1 apart. Now they're 4 apart. Okay? And that makes all of this, those characteristics like that. Okay? Maggie. You sure? You sure? Okay. Come talk to me about these. I know they're tough, but I do want to get through all the things for today. So go ahead and flip back to your notes for today. Your problem set is due on Monday. It's only a page front and back, so start early and make sure you're asking me any questions about that stuff. Today, we're going to talk about exponential growth and decay in like word problems. So looking at the way a population grows, or looking at the way money grows, or something like that. So to start off with, let's talk about money. We're going to talk about compound interest, which you can write down is how money grows over time. Raise your hand if you could tell me, like, anyone heard of interest before and could tell me what interest is? Jimmy?
Alright, so when you put money in your savings account over time, it gains interest, which gradually increases when you sign it.
Cool. So like for a bank to motivate you to put your money in their bank, in addition to like keeping your money secure, they offer usually an interest rate, which says just for keeping your money in our bank, if you don't touch it, then I'm going to take a percent of that and add it on what you have, so your money should grow over time. Cristobal?
What's the catch?
What's the catch? The catch is the money that you're giving the bank, they have in their possession for right now. So picture they got a bunch of people's money. So the way the bank makes money is while they're holding that, they use that money and get to like invest it and make money off of it themselves. So it's more of like, not a catch, but like an agreement. They're like, we'll hold on to your money for now and like use it while we have it, but anytime you need it, since we're also borrowing this guy's and this guy's and this guy's, we'll give it back to you, but we're gonna use it and make money off of it while we have it, yeah? And so they, to motivate you to go to Chase rather than like Bank of America or the next guy, they're gonna offer different interest rates to get, basically allow you to make like more money at their bank versus another one, yep? Which one's better? Depends. Depends on the latest offer and a bunch of things. Also, there's other factors like which one's close to your house and that kind of stuff. So there's a lot of things that go into it. But the cool thing for us to be discussing today, and unfortunately this is a very simplified version, we're not going to look at a lot of different cases of types of interest rates and things, but it is cool because understanding the math behind this, it actually does get pretty complicated. It does help you to make educated decisions about like when you see their advertisements or their flyers about different interest rates they offer, you could actually do some calculations to see like where would I make the most money, right? I'm at Chase, but I've just been at Chase for a long time. I probably honestly should do some research and see if maybe I could get a better interest rate somewhere else. Where I did have to do a lot of research was when my husband and I bought our house. Interest rates could be at a bank like this, which is what we're going to be talking about today, but notice another place that you pay interest, but you're paying the interest yourself, not the bank paying you interest, is when you take out a loan, which I had some people explaining today too. And so then I would want to see, like, where can I get the lowest interest rate so I'm not paying much on top of the money that I owe the bank, right? So there's different cases where we can talk about this. Okay, but we're going to look today at this formula. We're going to look at two. So first one up, Hertz, you might have heard of, A equals P times E to the R times T. You might have seen this before. This is a way for you to calculate your money after a certain amount of time if you have a continuous compound interest. If your interest is compounding continuously. In a second, we're going to look at a formula. Make sure you're still with me. In a second, you're going to look at a formula where it's not continuously compounded. It's compounded on like in fixed intervals. Okay? So this first one, the P represents the, I'm going to say like beginning amount. We call like our principal, the beginning amount that we're starting with. The R is our rate or the percentage that they give you that it's growing by. And the T is the amount of time that it's sitting there growing. Okay? So for this first problem, Christy's investing $300 in an account that has 6% interest. She's not making any other deposits or withdrawals because that would affect things. So assuming she leaves her money there, we want to talk about just how that money grows. What will her account balance be after 20 years if it's compounded continuously? So because it says it's compounded continuously, we're just going to use this formula. Okay, what are we going to plug in for her beginning amount? Josh, what's the beginning amount that it says that she has? 300 times E to the rate is not just going to be 6. Raise your hand if you know what we're going to write for our rate. Jesus? 0.06 because you move it over 2 spots. You're dividing it by 100 because percents are out of 100. Times our time, which is, we're doing 20 years right now. Okay? So you're going to just plug this in your calculator and find it. So I'm going to do a quick calculator check, walk around, make sure everyone has it while you're calculating. So go ahead and calculate that.
That is not honest.
Yep.
Would it be 1.06 or 0.06?
That's what you're going to be doing in the next formula. You're going to do 1 plus your rate. This one just your 6 money.
Oh, okay, so we're just finding the rate, we're not finding how much money we actually have. I'll go here.
We are. In this formula, this is going to find out how much money you actually have.
You just say 10 cents, 5 cents.
How much money?
I just proved you wrong, right? Right?
Yeah.
We're talking about something that we rock, right? No. I get a little
Hold on. Let me see. No. Do you have your marble card?
I've only got $15, but it's around
No, you're good already. Alright, you should have gotten $996 in if you round 4 cents, which for this one, usually we need to go 3 decimal places, but since it was money, I wanted to just go to cents, right? I wanted it to make sense with my units. So make sure for these problems, you're putting your units on the problem as well, okay? Okay, go ahead and try for me the next one. Actually, I'm going to cruise past this one. Again, it says compounded continuously, so we're going to use this formula right here, okay? For our next formula, this is going to be talking about not when we're going continuously. The continuous one we just talked about. Okay, it's written right here, but it's written with other letters. Notice this is the same thing as A equals P to the E or T, except they're using N and K and other letters, because this is the general one that you can use for population, not just money. Okay? Are these formulas the same? This one is just what they use for money with like principal and things like that. This one you can use for anything like a population. Alright? This is for when it's compounding continuously. If I give you a rate and I'm telling you that that rate is applied annually or at some specific time interval, okay? It's going to grow differently, and we're going to use this equation to help us, which still has a starting amount multiplied times 1 plus our rate raised to the power of time. And some of you might have seen this one as well. So if you look at this example, it says Mexico has a population of approximately 110 million. If it grows at a rate of 1.42% annually, predict the population of Mexico in 10 years and then in 20 years. Because it says 1.42 annually, show me on your finger really quickly, 1 or 2. Are we going to use the first equation up here or the second equation? Show me. Because it says 1.42 annually, based off of what I just talked about, which one are we going to use? Okay, I see a lot of 1s, a couple 2s. 2, remember, was when it's continuously, or like they don't have to say continuously, but it just doesn't, it's not over an interval, it's just a percent over time. That means continuously. This one is at a fixed interval. Annually, they're applying a 1.42 percentage rate, which means we're going with the first one. It's not continuous. So we're going to use this formula, N equals N naught times 1 plus R to the T. Plug in our values. What's our beginning population? We have 1 plus, okay, be careful for your rate. 1.42, move it 2 places, would be 0.0142, raised to the 10 years. Go ahead and calculate that for me.
It's continuous.
Not
Is it annually also continuous?
That's not to me. Yep.
What's the difference? I don't understand.
I'm gonna just give you 4 minutes, and if I start talking to you, I'll just end up talking to you, and I know we're gonna end, and I'm not gonna get to a decreasing example, so can we just like one off? I'm just gonna ask you one off with me, and then we'll talk about them, okay? The key thing to remember though is one of them is continuous, which means the rate, it's just growing every day in your bank account. The other one is an annual percentage rate, which means yearly, they're looking at the amount in your bank account and they're applying the interest on that year, rather than ever all the time. It's either growing all the time or it's growing on a fixed interval. But I'm gonna keep this going, okay? Okay, so we get 126.6569, which is 126.657 million people. Again, remember to go 3 decimal places, and unless it doesn't make sense for like money or something like that, okay? But you can have decimal millions of people, because this would be 126,627,000, etc. Okay? Okay, I'm gonna skip 20 years because we're just gonna plug in 20, right? Let's talk about one last example to make sure you see before we get out of here, about this population that is declining at a rate of 6%. Does it tell you that that 6% is on some fixed annual basis? No, it just says 6%. That means 6% all the time, so continuously. So we're going to use this second equation. And notice what I plugged in. I want you to raise your hand when you see something interesting about what I plugged in to the equation that you might have missed if you weren't paying close attention. Joanna, what do you notice? Why did I write a negative 0.06 rather than just 0.06? Leslie? This is exponential decay. It should be decreasing, which means I have to have, like we saw yesterday, a negative exponent. So my rate is a negative 6% rate. It's going down 6% rather than going up 6%. Okay? So watch out for which equation you're using. Watch out for if it's decreasing by the rate, because that's a negative number. Other than that, this is just plugging in numbers, right? Raise your hand if you feel like this is like a piece of cake, a problem like this, plugging in the numbers. Anyone? I feel like a lot of people that felt like that last year. The issue was on quizzes or tests, they didn't have these memorized, so all of a sudden it turned into a really hard problem when they didn't know the formula. So you need to know these 2 formulas, okay? Negative,
We said Wednesday. We have more time. I remember that.
Yeah.